I'm Jamie with Chegg Tutors. Today I want to talk to you about a class of organic molecules called cycloalkanes. These are alkanes, so they're just hydrocarbons. All they have is hydrogen and carbon at their most basic level, but they're arranged in a ring shape, like this cyclopentane right here. So first of all, I want to draw your attention to the way we draw cycloalkanes. So you'll notice, just like with other organic molecules, the simplest way to draw one of these is just to draw the shape itself. This is a pentagon, and this is cyclopentane. Each vertex is a carbon atom, and whenever the carbon atom doesn't have 4 bonds attached to it, we assume that the rest of them are hydrogens, because we know that carbon has 4 bonds always attached to it. So if we were to draw out this cyclopentane, it would look something like this. You can see how messy this looks, and not just because of my handwriting. So we really want to use a form like this, where everything is clean and clear, and we can really focus on the reactions and looking at the structure, rather than exactly what atoms are involved. This is especially important when you get into really big molecules, where this really does get unwieldy, and it's hard to see what's going on. So a little bit about naming. You always add a cyclo to the front of this, and that just indicates that it's a ring structure. You have the pent, or in the middle in this case, it could be a hex for hexane, or a bute for butane, 4 carbon atoms in the ring. And then you add the ane just for the alkane suffix, in other words, indicating that this hydrocarbon is saturated. You can't have any further hydrogens on this hydrocarbon. This is the most basic form, just if you have a ring structure with nothing on it. If you have something where, say, you added a ketone, so obviously you'd have 2 less hydrogens here, then this would be cyclopentone instead of pentane. It's not a cycloalkane, but it's still a ring structure, and that's an organic molecule. If instead you had an inorganic functional group attached, say you had a chlorine attached, you would call this chlorocyclopentane. If you had more than one thing attached, if you had 2 chlorines, you would number the things according to which you'd start with the molecule, or the carbon that has the most important functional group attached to it. So this would be 1, 2, 3, etc. You go around so that the attached things have the lowest numbers. This would be 1,2 dichlorocyclopentane. So we can add things to this cycloalkane structure and still know how to name them. And in fact, if we are reacting any kind of cycloalkane, we're going to have these extra functional groups, because by itself, just like any other hydrocarbon that's in a linear chain, these are not very reactive at all. Just one other note, the molecular formula for a cycloalkane that has N carbons in it, so this would be N would be 5 here, N would be 7 in a heptane, etc., in a cycloheptane. The formula is just CnH2n. And we see that because each carbon is attached to 2 other carbons, meaning each carbon has to have 2 more bonds, 2 more hydrogens in this case, to form 4 bonds at each carbon. This is a little different from a linear chain, where it would be CnH2n plus 2, because those carbons at the ends have 3 hydrogens attached, because they're not attached to each other. So the molecular formula will look a little different, and that's one of the ways you can tell that something is a cyclic molecule instead of a linear or a branched molecule. Now I want to just talk a little bit about how stable these cycloalkanes are. It really depends. So whenever you have a cycloalkane, the angle between the different carbons is totally determined by geometry. So nothing to do with chemistry here. Simply, if you have a cycloalkane that has 6 carbons, a hexane, it has to be a hexagon, and the angle between carbons in a hexagon of carbons is always going to be 120 degrees. Similarly, for cyclobutane here, the angle is always going to be 90 degrees. And that's how we can really tell how stable something is. Cyclohexane is really stable because remember, the ideal bonding angle for the carbon, if it was just going to be completely unstrained, is 109.5 degrees. So that's the angle for a tetrahedral geometry where there are 4 things around the carbon and no double bonds. So this 120 degrees is pretty close to the 109.5. There's very little ring strain here. This 90 degrees is really far from the 109.5. So you're going to see cyclobutane, but it's going to be much more reactive because it really wants to break this. This is called ring strain. So the most common cycloalkane you're going to see, or at least the most stable, is going to be the cyclohexane. Cyclopentane also comes pretty close. Cyclopentane actually has a 108 angle and is very stable as well. Cyclohexane is particularly stable because it can take on different forms. So it's not all in a plane here, and it can take on a form very close to 109.5 degrees. So this looks like a plane, and it is constrained by geometry, but it doesn't have to be in a plane. Something like cyclopropane, just 3, does have to be in a plane because it's a triangle. And this is the least stable cycloalkane because it has 120 degrees, rather 60 degrees between the different molecules, which is a tremendous amount away from 109.5. And there's no give. It can't go out of a planar structure to make it more stable. This is a brief introduction to cycloalkanes. I hope you'll find out more, but that's it for now, and see you next time.